All right, today we're going to unravel what is honestly one of the greatest detective stories in all of science. It's the hunt for the ultimate, fundamental building blocks of, well, everything. And what a story it is. It starts out with this beautifully simple idea, then just descends into total chaos, before finally emerging as one of the most elegant, powerful theories we've ever come up with. For just a brief, shining moment, we really thought we had it all figured out. We thought we knew what reality was made of. But oh boy, were we wrong. That tidy little picture, it was about to be absolutely shattered.
Okay, so let's set the scene. Let's go back to the beginning of this story, to a time when the universe seemed, well, it seemed to make perfect sense.
So picture this, it's 1932. The universe feels pretty simple. You've got the electron, you've got the proton, and the neutron had just been discovered. Throw in the photon for light, and that was basically it. It felt like we had the complete Lego set to build, well, everything. A really beautiful, elegant picture. And as we just said, completely wrong. The first real crack in that simple picture, it came later that same year. A scientist, Carl Anderson, he discovered something wild. The positron. Think of it as an anti-electron. This was our first real confirmation of an antiparticle. A particle with the exact same mass as an electron, but a positive charge. And you have to understand, this wasn't just another particle. This was a whole new kind of matter. And it basically opened the floodgates. So yeah, that simple picture was gone. Just poof! And in its place, physicists found themselves plunged into this period of just overwhelming, confusing, but also pretty exhilarating discovery. So first up, we get the muon. It acted exactly like an electron, except it was more than 200 times heavier. What? No one had predicted this thing. No one had any idea why it was there. It led to one of the most famous questions in physics history. From I. Rabi, who ordered that? And then came the pion, a totally different kind of particle. And it seemed to have a completely different job. Maybe it was the thing carrying the strong force, the glue that holds the centers of atoms together. After that, the kaon. And this one was just weird. For how heavy it was, it had a bizarrely long lifetime. It stuck around way longer than it should have. The list just kept on growing, and the confusion was getting deeper and deeper. And look, we're not talking about just a few new particles. We were cranking up these new particle accelerators, smashing atoms together with incredible amounts of energy, and out of all that debris came a flood, a complete deluge of new particles. We're talking hundreds of them. That clean, simple model of reality, yeah, it was now a total chaotic mess. This situation got so crazy that scientists came up with the perfect name for it, the particle zoo. And it really captures that feeling, right? Just being completely overwhelmed by this menagerie of weird, wonderful, totally unexplained new species of particles. And that's the big question, isn't it? How on earth do you find order in a zoo? Well, this is where the real detective work kicks in. Physicists started rolling up their sleeves and just sifting through all this chaos, hunting for any clue, any hidden pattern that could possibly bring some order to this particle zoo. One of the first big clues came from those particles we mentioned, the ones with the weirdly long lifetimes, like the kaon. So physicists proposed a new property for them, and they gave it this wonderfully whimsical name, strangeness. Here's the deal. These strange particles were always created in pairs. And this new strangeness number, whatever it was, it had to be conserved when the strong force was involved. Now that suggested there was a hidden rule here, some deeper structure they just weren't seeing yet. Okay, now this is where things get really cool. Two physicists, Murray Gell-Mann and Yuval Ne'eman, they started arranging all the particles in the zoo, but not by weight. They arranged them by their properties, like electric charge and this new strangeness idea. And look what happened. They just fell into these beautiful, perfectly symmetrical patterns. It was like a periodic table, but for subatomic particles. And just like the periodic table, it was practically screaming that these particles couldn't be fundamental. They had to be made of something even smaller. And that was it. That was the revolutionary idea that explained everything. The particle zoo wasn't a zoo at all. It was just a collection of different combinations of a few truly fundamental particles. Gell-Mann gave them a name. He called them quarks. And the system was so simple. The heavy particles, like protons, the baryons, they're made of 3 quarks. And the lighter particles, like pions, the mesons, they're made of 1 quark and 1 antiquark. Suddenly, the chaos made sense.
So this incredible insight that the entire zoo was just different quambos of quarks, it paved the way for the grand synthesis, the one theory to rule them all, the theory that finally tamed the particle zoo.
And here it is, the standard model of particle physics. All of that chaos, all of those hundreds of particles, tamed and organized into this single, beautiful, elegant chart. Every single piece of matter we have ever seen, ever detected, is made from these 12 fundamental particles. You've got 6 quarks up top, the things that build protons and neutrons, and 6 leptons down below, which includes our old friend the electron. And you want to know the most mind-blowing thing? Everything you see, everything you touch, you, me, the stars, all of it is made from just that first column on the left. The other 2 generations, they're just heavier, unstable copies that only really existed in the fiery chaos of the early universe.
But wait, there's more. The standard model doesn't just list the ingredients of matter, it also describes how they talk to each other. It explains 3 of the 4 fundamental forces of nature. See, each force is carried by a special kind of particle called a boson. You can think of them as little messengers running back and forth. The strong force has the gluon, electromagnetism has the photon, and the weak force has the W and Z bosons. The only one left out of the party? Gravity. It's the one big piece that still doesn't fit into this otherwise incredibly successful picture.
And yet, for all of its incredible success, the standard model still has some deep mysteries baked into it. Here's a great example. A proton, we know, is made of 3 quarks, and each of those quarks has a property called spin. Simple enough, right? Just add up the 3 spins and you get the proton's total spin. Except, you don't. When we do the experiments, the spins of those 3 main quarks only account for about 30% of the proton's total spin. So where in the world is the other 70% coming from? It's a puzzle we call the proton spin crisis, and it's a perfect reminder of just how much we still have left to figure out. And that really brings us to the frontier of physics today. The standard model is, without a doubt, a monumental triumph. But we also know for sure that it's not the final word. It's like having a beautiful, incredibly detailed map of a continent, but the map itself shows you that there are vast, unexplored oceans all around it. Here's one of those big, unanswered questions. The theory tells us that the Big Bang should have created equal amounts of matter and antimatter, and if that happened, they would have instantly annihilated each other, leaving behind nothing but a universe full of light. But, well, look around. We're here. The planets are here. The galaxies are here. So why? Why is there so much more matter than antimatter? The standard model? Well, it just doesn't have the complete answer. Okay, here's another one. The standard model pretty much assumes that protons, the very heart of every atom, are completely stable, that they'll last forever. But some of the newer theories that try to go beyond the standard model, they predict that protons should eventually decay. We're talking about timescales that are just ridiculously long, way longer than the current age of the universe. But still, right now, deep underground in giant detectors, scientists are watching trillions upon trillions of protons, just waiting to see if a single one will ever fall apart. So, this incredible journey from that simple little picture to the chaotic zoo and finally to this elegant model, it's not over, not by a long shot. The standard model is, hands down, the most successful theory in the history of physics. But it's incomplete. It leaves us staring at these huge, profound questions, and it's just waiting for the next generation of experiments, the next brilliant idea, to finally reveal what lies beyond, and to write the next chapter in our amazing quest to understand the universe.